Right. Last class we had this discussion that whether the pressure of liquid inside the pipe, okay, let's call it P1, will be greater, or the pressure of liquid after it comes out of the pipe, okay, P2 will be greater. Some of you were of the opinion that P1 will be greater than P2. Some of you said P2 will be more than P1. Okay. But basically, understand the problem here. You are asked to compare, or you are asked to decide where the pressure is greater in a given fluid, that is water in this case. Okay, water flowing out of the pipe. So if it is a continuous fluid, you can apply Bernoulli's equation, assuming it's an ideal fluid in steady flow. Okay. So using Bernoulli's equation, we will now derive mathematically which pressure is greater, right? So consider a situation like this. Basically, what is happening here, when it is flowing through the pipe, the water has a larger area of cross section. But when we partially close the mouth of the pipe, the water that is coming out of the pipe is coming out through a narrower area of cross section. Okay. So basically, it's a situation where the area of cross section is decreasing. Fine. If area of cross section is decreasing, we have to find out what happens to the pressure. And see, we are talking about pressure just inside the pipe, pressure of water just inside the pipe, and just when it is outside the pipe. So the 2 points, the black dot and the white dot that I have shown in this picture, are very close to each other. So they are almost at the same height from the ground. Why am I talking about height from the ground and all? Okay. The equation that we derived, Bernoulli's equation. What does the equation say? The equation says that the sum of pressure P plus rho GH plus half rho V square will be uniform in an ideal fluid undergoing steady flow, where H is height from the reference level for gravitational potential energy. So if you ever want to find out, or if you ever have to find out or comment on the pressure of a fluid which is flowing, or the height at which it is flowing, or the speed with which it is flowing, you will apply Bernoulli's equation, provided it's an ideal fluid undergoing steady flow. If they don't specify anything in the question, you will assume those conditions to be satisfied, because that is what is there in your syllabus. If they mention that it's a viscous fluid, then you will have to apply concepts of viscosity. Otherwise, you'll assume it's an ideal fluid in steady flow. So this is the equation: P plus rho GH plus half rho V square is equal to constant. Is equal to uniform, means that sum will be same everywhere. So if you want to compare pressures at two different points, you can use this equation. That is exactly what we are going to do now. When water flows out through the narrow cross section, you need to find out what happens to its pressure. So basically, if you think of it this way, let's call the pressure at this cross section as P1, pressure of fluid at this cross section as P1, and pressure of fluid at this cross section as P2. Okay, you can take it comfortably inside the pipe actually. This is just a part of the pipe. I'm not saying this is one end of the pipe and this is another end of the pipe. Okay, it's a long pipe in between which, it is changing its area of cross section. We are looking at a part of the pipe. Okay. Our job now is to compare these pressures P1 and P2 and decide which one is greater. Fine. So assuming it's an ideal fluid in steady flow, can one of you quickly tell me which speed will be greater, V1 or V2?
V2, sir.
V2, definitely. From equation of continuity, we know that A1 V1 is equal to A2 V2. There's one inlet and one outlet here. So V2 by V1 will be A1 by A2. A1 is greater than A2, so V2 will be more than V1. Where the pipe is narrow, the speed of flow will be greater. Okay. Now we need to compare the pressures. And we have one equation, Bernoulli's equation, which helps us include pressure, speed, and height into one equation. So what we are going to do is, we are going to write the sum. Okay, which sum? P plus rho GH plus half rho V square. We are going to write the sum of these three terms at the first point and equate it to the sum of these three terms at the second point. This is how Bernoulli's equation is applied. You choose 2 points in a continuous fluid and equate these sums at those 2 points. Okay. Now see, we considered a horizontal pipe here. In a horizontal pipe, the first point and the last point, they are both at the same height from the reference level, from the ground. Okay. Keep that fact in mind. And you know V2 is more than V1. Okay. Because where the area decreases, speed increases. So V2 is greater than V1 and you know it. So using these facts, find out whether P1 is greater or P2 is greater. Do this, both of you. I'll give you 1 minute. Right. I got one answer as P1 greater than P2. So basically, you're saying where the liquid moves slower, the pressure is higher, and where it moves faster, the pressure is lower. Okay. And that is correct. As we discussed yesterday, see, when water moves from broader cross section to the narrower cross section, its speed increases, means it accelerates. For something to accelerate, there must be a force in that direction. So in the broader part, there must have been greater pressure, and in the narrower part, there must have been lesser pressure. So fluid, as it moves from greater pressure to lesser pressure, is accelerating, is speeding up. Okay, and the equation also says the same thing. Let's write Bernoulli's equation. P1, pressure at the first point, plus rho g h1, height of the first point from the ground, plus half rho V1 square is equal to P2, pressure at the second point, plus rho g h2, height of the second point from the reference level, plus half rho V2 squared. Now we took a horizontal pipe. Okay. Even if the pipe is not horizontal, we are talking about pressure just inside the pipe and pressure just outside the pipe. So those 2 points are almost at the same height from the ground, irrespective of the orientation of the pipe. Okay. Just for us to visualize, I have shown this diagram. Okay. But actually what we are talking about is pressure of water coming out of a pipe through a narrow cross section. Okay. So the heights from the ground level are equal. These terms will get cancelled. Therefore, P1 minus P2 becomes half rho V2 square minus V1 square. And we know V2 is more than V1 in this case. So this is positive, greater than 0. That means P1 is greater than P2. Okay. So provided both points are at the same horizontal level, and it's a continuous fluid. Of course, the assumptions have to be satisfied. Ideal fluid, steady flow. Okay. If all these are satisfied, then where the liquid or fluid is moving slower, the pressure is greater. Where it is moving faster, the pressure is lesser. And this has very interesting applications. Okay. Let us next discuss applications of Bernoulli's equation. Right. One application of Bernoulli's equation you definitely need to know is this. Basically, it's about something called speed of efflux. Okay, that is nothing but the speed with which liquid flows out of a tank. Okay, so consider a barrel like this filled with water up to some height. Okay, and there is a tap, obviously, as you can see, the tap is closed. The level of the tap, or the level of the opening of the tap, I would say, is this, and the upper level of water is this. Okay, for now it is like this. Let this height be h, small h. It keeps changing as water gets drained. The height h up to which water is filled above the opening of the tap keeps changing. Okay. First of all, from your everyday experience, you all tell me, like when we open this tap, liquid will flow out, water will flow out. From your everyday experience, you tell me the speed with which water flows out when the tap is opened, will it always be same, or will it depend on the height of water in the tank or barrel? Once the tap is opened, the speed with which water flows out at a given instant, will it depend on the height of water in the tank, or will it not depend?
Thank you.
Venla, can you repeat? Depends or not depend? Depends. Okay. Aishwarya, what do you think? Okay, fine.
So depends on height.
Depends. Yes. From everyday experience, usually we get water from the overhead tank. When the overhead tank is full and you open the tap, okay, you see water coming out with a high speed. But as the water level depletes in the overhead tank, okay, the speed with which water flows out of the tap usually decreases. Okay. So that speed with which liquid flows out of a hole. Okay. They may use this term hole in the question. They may call it orifice. Okay. They mean the same thing. Or simply they can call it as a tap. The speed with which water or liquid flows out through the tap is what we call as speed of efflux. So we have to derive an expression for it. We know it depends on this height of liquid in the tank. How it depends on that is what we need to derive. Okay. Now, once we open the tap and the liquid starts flowing, is it static or dynamic? Once we open the tap and the liquid starts flowing, is it static or dynamic? Static means not moving with respect to container. Dynamic means moving with respect to container. It is definitely dynamic. Okay, once the tap is opened, it becomes dynamic. Okay. So here the fluid is static. Here it is dynamic. Okay. Dynamic means fluid is flowing. When fluid is flowing, you can't apply what you derived in fluid statics. What did we derive in fluid statics? Pressure, buoyant force. Okay. Those things you should not use here. Fine. Pressure at a depth and all, and buoyant force. All those things we discussed, that was in static condition. Okay. In dynamics, the only thing we derived so far, okay, the only two things we derived so far are equation of continuity and Bernoulli's equation. Those are what you need to apply here by assuming the conditions are satisfied. What are the conditions? Ideal fluid, steady flow. Okay. What do we want to derive now? The speed of efflux. So speed of fluid at one point is what we want. Does Bernoulli's equation include speed? Yes, it does. Okay. So we will consider this situation. The water level in the tank will keep changing. At a random instant, let that level be small h. Okay. What is Bernoulli's equation? P1, pressure at one point, plus rho g, h1, height of that point from the reference level, plus half rho v1 square is equal to P2 plus V2 square. Understand how I'm approaching the situation. Our aim is to derive an expression for speed of flow. Bernoulli's equation involves speed of flow. That's why I am applying that equation here. But there are a lot of other terms also in this equation which we need to take care of. Okay, let us do it step by step. What is the thing we want? We want the speed of flow here. Let's call it V2. You can call it V1 also, nothing wrong. It's up to you. You can find the speed of flow only if you know all the other things. So first of all, to apply Bernoulli's equation, you need to choose 2 points of the fluid where it is convenient to derive these terms or required to derive these terms. Now, water flowing out of the tap, that speed is what you need to calculate. So that second point has to be just outside the tap. You have no choice. Okay. Can one of you tell me any other point in this fluid or in this tank where you know the pressure, height, and things like that? At least a few of these, if not all of these. Where shall we take the other point to apply Bernoulli's equation between the 2 points? Do you know the pressure of this liquid anywhere? It's not a static
Sir, at the
liquid.
bottom one.
At the bottom of the tank. Okay. Vanilla, tell me, how much is the pressure of the liquid at the bottom of the tank? You are saying you know the pressure here. How much will it be?
So P naught plus rho GH.
See, that is what I warned you. P naught plus rho GH is applicable when the fluid is static. Here you should not use that. Is it clear?
Yes, sir.
అంతే కదా, the liquid is flowing here. You can't use P naught plus rho g h because the liquid may not be in equilibrium. అది కిందికి వచ్చే కొద్దీ, like water molecules as they come down, their speed may increase. Okay, so what's the guarantee that they are in equilibrium? We derived P is P naught plus rho g h by assuming that cylindrical column to be in equilibrium. Remember the derivations. Okay. I know others also will have this confusion, but if the fluid is flowing, don't apply P is P naught plus rho g h. Okay. So no, we don't know the pressure at this point. Is there anywhere else where you know the pressure for sure?
So the top point.
Topmost point, correct. Aishwarya, how much is the pressure at the topmost point?
Sir, atmospheric pressure.
Atmospheric pressure, correct. So what we are going to do is, see, even if it's a moving fluid, even if it is a dynamic fluid, if it's exposed to atmosphere, the pressure will be atmospheric pressure. Okay. So we are going to choose this as first point and this as second point. Okay. First point is the free surface of the liquid in the tank. Second point is the point where liquid comes out of the tap. Okay. Now, what is the pressure at the first point? Atmospheric pressure. Let me write that in the equation. Pressure there. Oh, pressure there is atmospheric pressure plus. Now in Bernoulli's equation, you have H1 and H2, which are basically heights from the reference level for gravitational potential energy. Where you take the reference height for gravitational potential energy is your choice. Okay. So you can take it wherever you want. To write the equation conveniently, okay, it is better to take the reference level at the point where water comes out of the tap. That level I'll take as a reference. I can take it anywhere else also. Okay, I'll show you both the approaches simultaneously. It won't make much difference. If you take this level as the reference, no, height of the first point will be h itself. Okay, so h1 will become h. And on the other side, h2 will become 0. Because water is coming out of the tap at the reference level itself. So that h2 will become 0 if you take it like this. Suppose you take the reference level somewhere else and call this height as h1 and this height as h2. Then what you will see is on one side of the equation, you will have rho g h1. On the other side, you will have rho g h2. Bring that term to this side. Ultimately, what you will be having is rho g into h1 minus h2. It's the height difference only that matters. Original heights don't matter. Okay. So where you take the reference won't matter. The difference in heights is h1, h, no? That is what matters ultimately. So let us follow the convenient procedure. Okay. Next, half rho V1 square. Now you have to imagine this liquid flowing. Here it will be flowing down through a large cross-sectional area. The area of cross-section here, you can call it as A1. Where it comes out of the tap, okay, where the liquid comes out of the tap, the area of cross-section A2 is narrow. Okay, there the speed is V2. At A1, the speed is V1. Okay, as water is drained through the tap, the upper level of water will be coming down. No? The speed with which the upper level of water comes down is V1. And the speed with which water leaves the tap is V2. Okay. So half rho, let's complete Bernoulli's equation, plus half rho V1 square. We don't know the expression for V1 or V2. Okay. Is equal to, next on the right hand side, you have P2. What is P2? P2 is the pressure of water when it just comes out of the tap. Can any one of you tell me how much it will be? Where water leaves the tap, how much will the pressure of water be?
You know,
Atmospheric pressure. Good. Because it is open to atmosphere. Okay. So P2 is also P naught itself. Plus rho g H2 we have written. Plus half rho V2 square. Since P2 is, since P naught is common, we can cancel it. Rho g 0 can be removed. You will be left with rho g H is equal to half rho V2 square minus V1 square. And density also gets cancelled now. You get V2 square minus V1 square is equal to 2GH. Okay. So if liquid is flowing down only because of gravity, right? A liquid which is exposed to atmosphere is flowing down because of gravity. V2 square minus V1 square will be 2GH. Okay. But still, we didn't get the final expression only for V2. This equation involves V2 and V1. Can any of you tell me another equation which involves V1 and V2? Any
Equation
equation?
of continuity, sir.
Good. Equation of continuity. And according to equation of continuity, A1 V1 should be equal to A2 V2. Fine. It's like liquid is entering in from here and leaving out from here. Okay. So rate of inflow is equal to rate of outflow. A1 V1 equal to A2 V2. Our aim is to derive V2. So we'll have to eliminate V1 from the equations. So you can write V1 is equal to A2 V2 by A1. And this we will substitute here. So what does the equation change to? V2 square minus V1 square becomes A2 square V2 square by A1 square is equal to 2GH. That means V2 square is equal to 2GH divided by 1 minus A2 square by A1 square, or 1 minus A2 by A1 whole square. Therefore, the speed of efflux becomes under root 2GH divided by 1 minus A2 by A1 whole square. Okay. See, you can remember this formula if you want, but remember the situation under which this was derived, or situation for which this was derived. This is for a tank which has one tap connected, one tap open. Okay, for that we got an equation like this for speed of efflux. Okay, again, from your everyday experience, any of you tell me, you might have seen overhead tanks, no, those Syntex. These days, many other companies are also popular, Astral and all. You might have seen those overhead tanks. Can any of you guess the area of cross section of an overhead tank? Those black or white tanks that you have at the top of the house or apartment. Rough estimate of the area of cross section of the overhead tank. Pawan, what do you say? ఎంత ఉండొచ్చు overhead tank cross sectional area? Okay. From what I observed, they have a radius of about maybe half meter, a diameter of about 1 meter, 2 meters will be there. So let's take a rough radius of 1 meter. If radius is 1 meter, then cross-sectional area pi r square. Pi is 3.14 into r square is 1. So 3.14. So around 3 meters square, let us take roughly. Okay, not all tanks are the same. I'm just taking a reasonable estimate. Okay, so cross-sectional area of the tank is this much. Suppose only one tap is connected to it. Can one of you guess the cross-sectional area of a tap, water tap? From everyday experience, just estimate the cross section. You should be able to do this, Miran. You want to become engineers or maybe doctors also, but you should be able to give a rough estimate of the area of cross section of a tap.
Sir, 10 centimeter.
10 square centimeters, you are saying. Okay. 10 is like around 3 into 3 or 3.1 into 3.2. Fine, it won't be that broad also. Okay. Let us take 10 centimeter square itself if you want. I would say 1 or 2 centimeter square, not more than that. Fine, let it be 10 centimeter square. Still, convert this to meter square. That becomes 10 into 10 power minus 4, which is basically 10 power minus 3 meter square. Now look at the ratio of these areas. One is 3, the other is 10 power minus 3. Okay. There's a huge difference. Okay. If you divide A2 by A1, the answer will be about 10 power minus 3. Or if you take A1 by A2, it will be about 1000 times. So area wise, the tank's cross-sectional area is about 1000 times the tap's cross-sectional area. So usually A2 will be very small compared to A1. Means cross-sectional area of the orifice or tap will be very small compared to the cross-sectional area of the tank. Under that condition, if A2 is very small compared to A1, then A2 by A1 will be very small compared to 1. Then what we can do is we can ignore this term. When you square it, it becomes even smaller. 10 power minus 3, if you square it, becomes 10 power minus 6. Whether you subtract 10 power minus 6 from 1 or not, it won't make much difference. So if you ignore that term, what does speed of efflux become? It will only be under root 2gh. And this is a very familiar expression, V is equal to under root 2gh. Can any of you tell me where we Okay. Can any of you tell me where we came across this expression V is under root 2GH before? Do you remember using this expression anywhere under root 2GH for speed?
It's the speed of free falling ball.
Speed of freely falling ball. Okay. If an object is dropped from rest, then when it comes down by a height h, the speed becomes under root 2gh. Okay, good. So if a2 is very small compared to a1, the speed of efflux becomes under root 2gh. Right. What is h here? H is the height difference between the tap's opening and the tank's opening. And remember, here we assumed it's an open tank. That is why P1 was equal to P0. If it's a closed tank, you will have to deal with it differently. Okay. Next, we assume the water is open to atmosphere when it comes out of the tap. If it's not, suppose it's connected to another pipe or something, then you won't be able to use this directly. Without knowing additional information, you won't be able to use this. Fine. So remember the conditions under which what you derived is applicable. This is most important if you are preparing for mains or advanced. Okay. Fine. So basically, this is what we call as speed of efflux. And if this condition is satisfied, if the area of the opening is very small compared to the area of the tank, then the speed of efflux becomes under root 2gh. This equation is called Torricelli's equation. Okay, but it's derived using Bernoulli's principle. Suppose the area of the tap, okay, area of cross section of the tap is not very small compared to the tank. Then you will have to use this equation as it is. So remember the original equation also. Okay. Let's solve some problems based on it. Just a moment. Observe the equation that we derived. The speed of efflux is under root 2gh or under root 2gh by 1 minus a2 minus a1 whole square. Look at how it depends on the height. H is in the denominator. Sorry, h is in the numerator. As height decreases, the speed of efflux also decreases. And that is what we observe in daily life also. Of course, in daily life, real water is a viscous fluid. It's not an ideal fluid. And there's no guarantee that it undergoes streamline flow also. So these are just ideal estimates. Okay, you can't directly apply this to a real life situation. Some adjustments will have to be done, but it definitely depends on height. Okay, so consider a tank like this. Assume this tank, okay, assume the height of liquid in this tank is initially capital H. Okay, now when you remove the stopper and water starts flowing out, liquid starts flowing out, that height will decrease. If height decreases, the speed of efflux also changes. And as time passes, after some time, the height will change to some other value, okay, maybe like half or so on. So what we need to derive is the time taken for half the liquid to get drained. Okay, and assume area of cross section of the tank is capital A, area of cross section of the tap is small a, and small a is very small compared to capital A. Okay, that is given to you. And if required, consider, okay, I don't think density will matter. No, density does not matter. Areas of cross section are given to you. Initial height is given to you. Fine, I think you will be able to solve this. So after the stopper is removed, you know water will flow out of the tank. You need to derive an expression for half the tank to get emptied or half the liquid to get drained. So tell me some ideas. How can we start solving this problem? First of all, after the stopper is removed, it becomes a dynamic fluid. First, any one of you tell me, what do we know about dynamic fluids so far? What are some equations we know about them? Dynamic fluids means flowing fluids.
So equations of continuity and Bernoulli's equation.
Okay. Equation of continuity we know. Next, we know Bernoulli's equation. And by applying Bernoulli's equation to this, we even derived speed of efflux. Okay, so these are the things we know so far about dynamic fluids, especially this case, we know speed of efflux also. Okay, speed of efflux is nothing but speed of flow. How can we make use of speed of flow to find out time taken for something to happen or time taken for a certain volume to escape? How can we link speed of flow to volume flow? How to link speed of flow to rate of flow of volume? What is the formula for volume flow rate through a cross section? We had derived this just before deriving equation of continuity. Okay,
So velocity into area of cross section.
correct. So speed of flow multiplied with the area of cross section gives us the volume flow rate. That is volume flowing out per unit time. So speed can be related to volume flowing per unit time, and from that you can find out the time taken for a certain volume to escape. That is the procedure to be followed in this or to solve this problem. Okay. So let's think a little further. As we open this stopper and liquid flows out of the tank, one of you tell me, do you think the speed of flow will be constant? Means will it be same at all times or will it change from time to time? The speed of flow of liquid from the tap, will it be constant or variable? Variable, okay? Because speed of flow depends on the height of liquid above the tap. Height will keep changing as the liquid gets drained, that height will keep decreasing, so speed will keep changing. So if speed is variable, volume flow rate will be variable. So let's write a rough equation. Let's say R is equal to rate of flow of volume per unit time. So you can say the small change in volume or the small volume that flows out in a certain interval of time, in a short interval of time, is that rate multiplied with dt. We don't know the rate yet. Okay. So if you want to find out the time taken for volume to change by a significant amount, then you will have to integrate both sides. Integral small changes in volume will become the total change in volume, or the total volume that escapes will be equal to integral of rate of escape of volume or the rate of flow of volume dt. Okay. Here R is a variable, so you can't put it out of the integral. The rate of flow becomes variable here. Why? Because the speed of efflux is a variable. So do this, all of you. I think I have given you sufficient hints. Take a screenshot of this quickly. Area of cross section of the tank is capital A. Area of cross section of the tap is small a. Height of liquid initially is capital H. Okay. We know that height keeps changing. So first, consider height as small h, which is basically a variable. So we don't know this. But what are the limits? It varies from initial height is capital H. What do we want to find out? We want to find out the time taken for half the water to get drained. And this is a tank of uniform area of cross section. If area of cross section is uniform, for half volume to go out, half height has to decrease. Okay. So limits will be from h to h by 2. So consider height as that much. What I want you to do is write the expression for speed of efflux. Once you know the speed of efflux, write the expression for rate of flow of volume. Once you know rate of flow of volume, after that, you need to do this. That rate you'll have to integrate with respect to time. Okay. Do this, all of you. I'll give you 3 minutes. After that, we'll discuss the solution. Okay. In terms of small h, see, we know that speed of efflux is going to be under root 2gh. Why? Because it is given to you that the area of the tap is much smaller compared to the area of cross section of the tank. So Torricelli's equation will be applicable. Under root 2gh is the speed of efflux. Okay. If you know the speed of efflux and you know through what area the liquid is flowing out, can one of you tell me the expression for volume flow rate in terms of what is given in this diagram and the speed of efflux, of course? How do you express volume flow rate from this tank? Aishwarya, how do you write volume flow rate in terms of speed of efflux? No response. Vanilla,
Sir, root 2GH into A,
which A?
capital
Speed of efflux is speed at which cross section? Capital A or small a?
small s.
And then you have to take that cross section area only, no? So basically volume flow rate is given by volume flow rate through a cross section is given by area multiplied with the speed of flow. Area of cross section multiplied with the speed of flow at that cross section only. Now we know speed of flow through the tap. Okay. That is under root 2GH. Then you have to multiply it with area of cross section of the tap itself, not somewhere else. So this is the rate of flow of volume. You can say this is the rate at which volume flows out of the tank. Okay. Now, if volume is flowing out of the tank, what happens to volume left inside the tank? It will decrease. If liquid is flowing out, volume of water left inside the tank decreases. So you can say A multiplied with under root 2GH is negative of rate of change of volume inside the tank. Because volume in the tank is a decreasing quantity. Derivative of a decreasing quantity will be negative. Negative of negative will become positive. A root 2GH is a positive term, no? So if you want to relate that to rate of flow of volume or rate of change of volume in the tank, this is how you do it. Is this step clear to all of you? Any doubt in this? Why I put the minus sign? Okay. Now what is it that we want? We want the time taken for height to decrease by half. Okay. Volume to decrease by half, which means height has to decrease by half. Keep in mind, we are considering a tank with uniform area of cross section. That is why half volume means half height. Okay. So you have to keep the h terms on one side, height terms on one side, and t terms on the other side. So how do you do that? A multiplied with dt becomes negative of change of volume in the tank divided by under root 2gh, where small h is a variable. Of course, volume of liquid in the tank is also a variable only. So one of you tell me at a random instant, suppose the liquid is only up to this level. Okay, let's say only this much liquid is left, where the height is small h. How much is the volume left in the tank? If the height is small h, how much is the volume of liquid remaining in the tank? This is quite easy.
A into H, sir.
Capital A into H, correct. Okay. So volume of liquid left in the tank is capital A multiplied with small h. Fine. So you can say that A dt is equal to negative of, now capital A cross-sectional area of the tank is constant. Keep it outside. Minus A by under root 2g also you keep outside. H and root h. One root h will remain in the numerator. So d of root h you can say. Okay. Is this clear to all of you? Fine. If you have any questions anywhere, you can ask. Right. D of root h is nothing but small change in root h. Now integrate both sides. Okay. Integral dt becomes t or delta t, the total time taken for the change in height to take place, minus a by under root 2g. You are integrating d of root h. Okay, this is a slightly tricky integration. Dx means what? Change in x. Integral dx becomes total change in x, which is x final minus x initial. Similarly, integral of derivative d of root h simply becomes root h final minus root h initial. That's all. Okay, think of root h as one term. You are integrating the changes in root h, small changes, you'll get the total change in root h. So basically it becomes under root h final, just a second, under root h final minus under root h initial. If you include the minus sign, or if you send the minus sign inside, it becomes a delta t is equal to capital A by under root 2g into root of h initial. Initial height in the tank was capital H minus root of h final. Final height in the tank is h by 2. According to this question. In another question, they may ask you h by 3, h by 4, whatever it is. But this is the approach. That's all. And that is the time it takes. Okay, let's go through this once again. You had to find out the time taken for half the liquid to get drained out of the tank. Means volume has to decrease by half. Why should the volume change? Because obviously it is leaking out of the tank. We only know speed of efflux. So that means the speed with which water flows out of the tank. Using that speed, we had to find out time taken for volume change to happen, certain volume change to happen. So we link speed to rate of change of volume, and then we adjust the equation and integrate. That's the logic here. Okay. You can take the time, now you can tell the time taken for 1/4 of the tank to become empty. You can tell the time taken for 3/4 of the tank to become empty and so on also. Right. Let's consider another situation slightly related to this. Assume there is a smooth horizontal surface. Okay. Let's say you place this tank on that smooth horizontal surface. Right. Initially, the tap is closed, so water will not be leaking out, and assume the tank is in equilibrium. Fine. And let's say density of liquid is rho. To answer this question, density will be needed. Now we had considered the balloon example in the last class. If you suddenly open the mouth of a balloon filled with air, air leaks out in one direction, balloon body moves in the opposite direction. The same thing can happen with this tank also if the surface is perfectly smooth. Okay, the moment or after you open the stopper, water will start flowing out to the right side. The tank will start moving to the left. Okay, hope you all are able to imagine this happening. If air leaks out from one side, balloon moves to the opposite side. Same thing happens with this water tank also. Okay. Let us ignore the mass of the body of the tank. Let's say water mass is quite large compared to the tank's mass. So overall mass of tank plus water is the mass of water itself, almost equal to mass of water itself. Let us consider that condition. So tank is initially in equilibrium. I want you to find out when the stopper is removed. First, write an expression. You can derive the expression for acceleration of the tank. Okay. Try this, all of you. I'll give you all 3 minutes again. So I want you to find out just when the stopper is removed, what is the net force and acceleration. Time to time, it keeps changing. Okay. Why it changes from time to time, we'll discuss. But at the initial instant, you all derive this. Try. Listen. The tank is initially in equilibrium. Even when liquid leaks out of the tank, the external forces acting on tank plus liquid system are weight and normal force from the surface. Weight and normal force from the surface are both in the vertical direction. So whether they are balanced or not, horizontally the net force is zero. And if net force is zero, you can apply conservation of linear momentum. Why am I talking about conservation of linear momentum here? That is because the tank starts moving due to the water flowing out. Okay. Now we had discussed this before also. If motion of one part of a system affects the motion of another part, in such cases, you will think of applying linear momentum conservation. Okay. So basically, just when the stopper is opened, whatever is the momentum the water carries in this direction, the same amount of momentum the tank will attain in the opposite direction. Therefore, dp by dt of water flowing out will be equal to dp by dt of the tank, which is nothing but force acting on the tank. That's the idea. Simple. Okay. So we have to find out the rate of flow of momentum just when the stopper is removed. I think this is easy. You all can manage. The speed of efflux we know is under root 2gh. We are still working under the assumption that small a is very small compared to capital A. So the height initially is capital H. So speed of efflux is under root 2g capital H. If you know speed of efflux, volume flow rate is cross-sectional area multiplied with speed. We know this with volume flow rate, rho AV, that is rho A into under root 2gh. And if you want momentum flow rate, this also we have derived. dp by dt is rho A V square, mass flow rate multiplied with the speed. Okay, rho A V square simply becomes 2g capital H. This is the rate of flow of momentum to the right side. Same will be the rate of increase of momentum to the left side because net momentum should remain conserved. Okay, so this basically is the net force acting on the tank horizontally. Fine. If you know net force, you can write the expression for acceleration. F net is equal to mass into acceleration. So rho small a 2gh net force is equal to, one of you tell me how much is the mass of the tank? I told you the mass of water in the tank itself is the mass of the tank. So how much mass, how much is the mass of water in the tank?
Rho A H G.
Can you repeat? It was not clear.
A H into G.
Okay, I asked only for mass. So density into volume, rho A H. Okay, so mass will be rho capital A into H. That is mass multiplied with acceleration. Acceleration, let's call it as A dash. That's all. Rho gets cancelled, H gets cancelled. Therefore, acceleration just when the stopper is opened is 2g small a divided by capital A. That's all. That's the acceleration of liquid in the tank when the stopper is just opened. After some time also, if you want, you can find out. Okay. You need to know the speed of efflux at that time. With speed of efflux, you will write the expression for rate of flow of linear momentum. You will get net force. Based on that, you can get the acceleration. Okay. But let's see. If you consider a random instant later, okay, at some instant, at some later instant, the speed of efflux will be under root 2g small h, where small h is the height of water left in the tank. Okay. Therefore, rate of flow of momentum from the tank will be rho small a v square, that is 2g small h. And you equate this to mass into acceleration. Mass will be rho a small h multiplied with the acceleration. This way, if you do, you will see that the acceleration by capital A, same as what it was initially. But there is a flaw in this. Okay. This procedure, I mean, there is a mistake in this procedure. Can any of you find out what is wrong with this? The acceleration will not be constant. Okay, but if you do it this way, you will see, I mean, you will get it as if it is constant. It's the same at all heights. There is something wrong in this. Can any of you identify what is wrong in this? I'll give you all a minute. Think about it. Any answer, anyone? What is wrong with this? Okay. See, initially the tank was in equilibrium and it was at rest. Net momentum was 0. Okay. So how much ever is the momentum gained in one direction, same will be the momentum gained in the other direction. But later on, the tank will be moving. So net initial momentum is not 0. So the way you apply momentum conservation has to change. You can't write momentum of water going to the right side is equal to momentum of tank going to the left side. That will not work later. Initial instant it will work. When the first element of water comes out, okay? whatever momentum that element carries, the same momentum the water tank will carry in the opposite direction. So for the first element, it is valid. Later on, it will not be valid because later on the tank will already be moving. For the moving system, you'll have to apply linear momentum conservation. Okay. That is, for now, it is beyond the scope, okay, of these classes. I'll give you a worksheet based on that. You can try it out on your own. So let's summarize what we discussed today. Basically, we are dealing with applications of Bernoulli's equation. So where do you apply Bernoulli's equation? Wherever or in any situation where there's an ideal fluid in steady flow, you can apply Bernoulli's equation. Okay. So in questions where you're asked to comment on or derive speed, pressure, height, you can apply Bernoulli's equation. Okay. And based on pressure, you can tell force also. Based on speed of flow, you can tell force. Of course, there are different kinds of forces. Based on pressure, the force you find out is the force perpendicular to a surface. Based on speed, the force you find out is the force acting on a cross section. Okay, on an opening of the tank or something like that. So such questions you can apply Bernoulli's equation. So we applied that too. Find the speed of efflux or derive an expression for speed of efflux first. And using that, we solved some problems, right? Next class you'll have tomorrow itself. And in tomorrow's class, we will discuss some more applications of Bernoulli's equation. There's one application, Venturi meter, which is very much part of your syllabus. We'll also solve some more problems. So next class will be all about application of Bernoulli's equations. Okay, equation. Thank you all. We'll continue tomorrow.